Derivatives of polynomials and exponential functions. We're going to start with the derivative of a constant. So if you have a number, you have a horizontal line. Slope of a horizontal line is 0. If you have x to a power, then we're going to apply what's called the power rule. Power comes in front, and then drop the power by 1 for the x. Constant multiple rule says if you have a constant in front, it gets carried along with the derivative. Sum rule, difference rule, same as with limits, you can do them individually. And the last is the derivative of the natural exponential function. So this is e to the x, the easiest derivative in calculus. It's itself. New vocab, normal line, and the normal line is perpendicular to the tangent line. To practice these, we're going to start with negative 2x to the fourth. Negative 2 is a constant being multiplied. It gets carried along by the derivative of x to the fourth. Exponent goes in front, reduce the exponent by 1. We get negative 8x to the third for its derivative. Number 9, we have a combination of a difference rule and a sum rule with constant multiple and powers. If a constant is in front, it's getting carried along. So the 3 goes down in front by the power rule to make 18x to the decrease by 1 power. Minus, this is x to the first, 1 comes down in front, technically x to the 0 left, which is 1. Constant function is 2, its slope is 0. F prime in my next one is all terms dealing with the power rule and constant. 8 comes down in front. I'm going to make 6x to the 7th minus 6 comes down in front to make 14x to the 5th. Constant by itself goes to 0. If you have a function that any term is not written as x to a power or recognizable, you do a rewrite first to make life easier. This square root of x is x to the 1/2, so now I can apply the power rule to it. F prime is going to equal 3 times easiest derivative of all is itself plus 1/2 x to the negative 1/2 minus 5. In the following derivatives, our input is no longer going to be x. We're going to change it to something else. If the input is changed, that is okay. You just have to treat it as if it was an x. In this first example, I have a product, but I don't have a product rule. That means I'm going to take and apply some algebra rules to condense it and get t to the negative third plus bt to the negative 1. Now I have two terms that have powers, and this is not t, so it's treated as a constant being multiplied because I am differentiating with respect to t. So g prime of t is going to equal negative 3t to the negative 4 minus bt to the negative 1, or negative 2, sorry. M, rewriting first, so I have powers would be 7a to the negative 4 thirds minus e to the second. Differentiating with respect to a now, so the variable input is a. That's being treated as if it was an x. Negative 4 thirds in the front to make negative 28 thirds, a to the negative 7 thirds. Minus e squared. Notice there's no a in here. This is treated, this is a constant. If it doesn't work for you that way, you throw the a in, and technically it's a to the 0. If I multiply 0 by the front, I'm wiping the whole thing out. Either way will get you that answer. Function h is written in terms of p, So I'm going to simplify these all down because I don't yet have some kind of a quotient rule. 1p to the negative 1/2 minus 2p to the half plus p to the 3/2. H prime, differentiating with respect to p, gives me negative 1/2 p to the negative 3/2 minus p to the negative 1/2 plus 3/2 p to the 1/2. C is written in terms of x and y, but we care about differentiating with respect to y. I see it's being squared, so of course I'm going to do my algebra first so I can analyze things term by term. X squared plus 4xy cubed plus 4y to the 6th. Differentiating with respect to y. No y's exist here. That's treated as a constant. It goes to 0. 4x is a constant multiple in the front. 3 times 4x gives me 12xy to the 2nd. Plus 6 times 4 is 24y to the 5th. Analyzing 16, I see a second derivative. I can't just jump to a second derivative because I'm finding slope of a slope graph. I'm going to rewrite y as 8x to the 1/2. I can then find its derivative, which would be 4x to the negative 1/2. The second derivative would be negative 2x to the negative 3/2. I need the second derivative at 4. I can use a little bit shorter notation, means the same thing, and find negative 2 times square root of 4, 2, cubed 8, flip it 1/8. So I get negative 1/4 for that second derivative value. I'm looking at 4x to the 4th plus x, and I'm seeing a tangent line here at 0, 0. We're going to find at what point is the tangent line to the graph perpendicular to the line tangent at 0, 0. So here's my tangent line at 0, 0. I want to be perpendicular. So I start thinking, drawing things that are perpendicular, but I'm trying to get to a point where I match the slope. Right here is looking pretty good as far as matching the slope. And it looks perpendicular to the tangent line at 0. So I'm aiming, it's probably right about here. If I'm talking about a tangent line to a graph, then I'm matching the slope. Slope is the derivative. I'm going to take 16x to the 3rd plus 1 as the derivative function of y. I'm finding the slope at 0. Y prime at 0 is going to equal 1. I want to be perpendicular to the tangent line. Perpendicular means opposite reciprocal slope. So I'm going to take negative 1 and set it equal to my 16x to the 3rd plus 1. Solving, move over, negative 1/8 equals x to the 3rd. Negative 1/2 is equal to x. Plug that back into y, because I'm looking for the point that this occurs, and I get negative 1/4. So my ordered pair is negative 1/2, negative 1/4. Finding a and b so that the line y equals negative 3x plus 4 is tangent. Tangent means touching and matching the slope at a particular point. In this case, it's 1 to this particular curve. I'm going to, because it's tangent line, that means I match slopes. I'm going to take the derivative as a first step. A and b are constant multiples. So I have 3ax squared plus b, as my derivative formula. If its tangent, it's matching slopes, and the slope of the tangent line is -3. This is occurring at 1, so I get -3a plus equals 3a plus b. That's one equation, two unknowns. I'm going back to the fact that I know I have a tangent line at 1, and this is the tangent line. Y at 1 equals -3 plus 4. Y at 1 is equal to 1. I can use that point now in my cubic. 1 equals a plus b. Two equations, two unknowns. Let's bring them together. 3a plus b equals -3. A plus b equals 1. Let's subtract for the system. 2a is equal to -4. A is equal to -2. Found the a value. For the b value, -2 plus b is equal to 1. B is equal to 3. And there we go. Page 3, finding the equation of the tangent and the normal line to this particular function. And we're going at 8, -20. Tangent line, matching slope, and having the same point. I'm going to take f of x, and I'm going to rewrite it so it's easier to apply the power rule. 6x to the 1/3 minus 1/2 x squared. Tangent line, matching slope. Let's figure out the slope. We end up with 2x to the -2/3 minus x to the 1st. Finding the slope at 8 is going to give me 2 times cube root of 8 is 2, squared is 4, flip it, I get 1/4, minus 8. 1/2 take away 8 is the same as saying 1/2 take away 16/2, so I get -15/2 for the slope value. I got a point and a slope. Tangent line is going to be y plus 20 equaling -15/2 times x minus 8. The normal line is the opposite reciprocal because it's perpendicular. Y plus 20 equals 2/15 times x minus 8. A little physics review. The position of a body at time t seconds, we have a function here for position. It's a cubic function. Find the body's acceleration each time velocity is 0. Connection is velocity equals derivative of position. My velocity function is going to equal 3t squared minus 12t plus 9. I have to eventually deal with acceleration, but it's each time the velocity is 0. So I'm going to go 0 equals, to find those times, 3 times t squared minus 4t plus 3. Factoring further, I have t minus 3, t minus 1. The two times are 1 and 3. Acceleration is defined as the derivative of the velocity. So my acceleration function is 6t minus 12. Acceleration at 1 is equal to -6. Acceleration at 3 is equal to 6. Let f be defined as this piecewise function, and we're going to find the values of a and b so that f is continuous and differentiable. I'm going to start with continuity. If it is continuous, that means your pieces have to be joining together. So I'm going to say x squared plus 2 is equal to a times x minus 1 over x plus b. Well, where are they equal? They have to be equal where we're defining them at 1. 1 plus 3 is equal to a times 1 minus 1 plus b. Oops, a little mistake here, kind of jumping the gun. 1 plus 2 is 3, that goes to 0, and b equals 3. From there, I'm going to take and rewrite f, because if we're talking about differentiability, I want to be able to take the derivative of this. So let's get f into a format that is easy for us to take a derivative. I'm going to distribute the a, it's a constant multiple, through. So I have ax minus ax to the negative 1 plus 3. These are my two pieces, for x is less than or equal to 1, and for x is greater than 1. I want to do f's derivative for each of these pieces. Top piece would go to 2x. Bottom piece is going to be a plus ax to the negative 2. Now, we're concerned with being differentiable. Linear function is differentiable. This reciprocal and a constant is differentiable. The question is at 1. So I'm going to say for x is less than 1, and I'm going to say for x is greater than 1, because at 1 we have to know, is it coming together with the same slope? I'm going to take my two pieces and plug in the 1 to see. 2 times 1 is equal to a plus a times 1, which is a. I get 2 is equal to 2a, 1 is equal to a. So when a is 1 and b is 3, then my function f is continuous and differentiable. I have another piecewise function here, and I'm looking at, is this function differentiable at x equals 2? Well, let's take and look at each of the pieces. If I take my derivative first, the top piece goes to 2x for x being greater than 2, and the bottom goes to 4. It's a linear function, and I'm going to say right now for x is less than 2. The question is what's going on at 2. So to approach it, we're going to use limits from our past, and we're going to approach 2 from each side. So if I take and approach 2 coming from the right on the derivative, I'm going to get a value of 4. If I take and I approach 2 from the left on f prime, that's the constant, that's 4. So far I have a match, so it's looking pretty good. The only thing is, in order to be differentiable, I also have to be continuous. So the next thing I need to do is to look, the limit as x approaches 2 on f of x to make sure each piece is coming together and I'm continuous. If I look from the right, I am plugging into x squared. 2 squared is equal to 4. If I take the limit as x approaches 2 from the left of f, that's 4 times 2 is 8 minus 4, which is 4. We're in good shape because f is continuous at 2. So yes, f of x is differentiable at x equaling 2. I would pause the video, try the multiple choice, and then come back and listen. For the first one, we're talking about a limit, but I'm noticing in that setup it looks very familiar, like a problem we've seen before. And that one is saying I have a function, and if I do x plus h to the fifth minus f at x, something to the fifth, 2 plus h is a little bit more, so my function is going to be x to the fifth. It's raising things to the fifth power. If I take the derivative using my shortcut rules, this is pretty similar to finding this one at x. I want to find it at 2. So I'm going to plug 2 into my derivative formula, and then I'll have it exactly. So that becomes 5 times 16, which is 80. So we're not doing these limits out. Nobody wants to raise that to the fifth. You want to recognize them. My next one, my function to recognize is I'm doing a square root of an input, and my input is x. It'll change in the limit, but I'm saying it's a square root function plus the squaring function. Both of these are coming into play. That's the limit notation, which is the setup for the derivative. So I'm going to take the derivative of each term, and then if I evaluate the derivative at 9, I get a half times a third plus 2 times 9 is 18. So we're looking at 18 1/6 for the total.